In this section, we're going to be looking at polynomial and rational inequalities. And out of that section, we're going to be doing two things: solving polynomial inequalities and solving rational inequalities. Okay, we'll define what a polynomial inequality is. It is any inequality that can be put in one of the forms. Either f of x is less than 0, f of x is greater than 0, f of x is less than or equal to 0, or f of x is greater than or equal to 0, where, in this case, your f is a polynomial function. So a polynomial inequality is going to have one of those four different forms. Now let's look at the procedure for solving a polynomial inequality. We first express the inequality in the form f of x is less than 0, or f of x is greater than 0. Then the second step will be to solve the inequality f of x equal to 0. Now the real solutions are going to be considered your boundary points. And then step number 3 is to locate those boundary points on a number line. That's dividing the number line into intervals. And then the fourth step would be to choose a test value within each interval, and you're going to evaluate f of x at that particular number. If the value of f of x is positive, then that means that f of x will be greater than 0 for all of the numbers in that interval. Or if the value of f is negative, then that means that f of x will be less than 0 for all of those numbers in that interval. And then step number 5, you're going to write the solution set or the intervals that will satisfy that given inequality. And keep in mind that procedure is going to be valid if you had less than or equal to and greater than or equal to. But with less than or equal to and greater than or equal to, you're going to include your boundary points in that solution set. Okay, we're going to look at a couple of examples that are like that. Let's say we want to solve and graph the solution set. In this case, we got x plus 3 times x minus 5 is greater than 0. Okay, now I'm going to move some of this stuff out the way so you can see this. So here we're going to solve this polynomial inequality. X plus 3 times x minus 5 is greater than 0, and graph the solution set. Now here we're lucky because this is already factored for you. There will be some problems where you may have to do some factoring before you go on to this step. What I'm going to do here is treat this as x plus 3 times x minus 5 equal to 0. And then we're going to set each binomial factor equal to 0 to find out what our boundary points are going to be. So here we got x plus 3 is equal to 0, and then x minus 5 is equal to 0. Each one of those will solve for x. So for x plus 3 is equal to 0, you'll have x is equal to negative 3. And then for x minus 5 is equal to 0, you'll have x is equal to 5. So x equal negative 3 and x equal 5 represent the boundary points that we will be using. Okay, so if we were to graph this on the number line, here's negative 3, and here's 5. Now in this case here, we're going to use open circles at negative 3 and 5. The reason for that is it just says greater than. That means that the negative 3 and negative 5 will not be included in the solution set. Okay, so that tells me I have these intervals. I have 3 different intervals because I have 2 boundary points. That means I have 3 intervals. One of them is from negative infinity up to negative 3. The other interval is between -3 and 5. And the other one will be from 5 up to infinity. Okay. Those are my three intervals that I have here. So if you look at the number line, I have 2 boundary points. That means I have 3 different intervals, as I'm indicating here. Now the next column, now notice I'm doing a table. The next column is going to be a test value. I'm going to pick a test value that is within each one of these individual intervals. And then I'm going to evaluate f of x. That's going to be the third column, and the final column will be the conclusion, whether it's positive or negative. And it depends upon f of x. Now, let's start with -infinity to -3. That's this first interval right here. A good test value for that would be, let's say, -4, because -4 is in that interval. So I'm letting x equal -4. And then I'm using this equation to find out what f of x is, because this part represents f of x. We replace each x with -4. So -4 plus 3 will be -1. And then -4 minus 5 will be -9. So I have -1 times -9, which will be 9. Keep in mind I'm replacing the x with -4. So -4 plus 3 is that -1. And then -4 minus 5, which is -9. So -1 times -9 is +9. And it is a +9, so that means this interval, all the f of x values within that interval from -infinity to -3 is positive. Now for -3, 5, that's this interval right here, a good test point would be x equals 0. Because if I do this 0 plus 3, that's 3. And then 0 minus 5, that's -5. 3 times -5, that's 15. And -15 is negative, so that means between -3 and -5, all of my f of x values will be negative. And then finally, 5 to infinity, that's this interval right here. A good test value, let's say x equals 6. Okay, and then replace each x with 6 here. So 6 plus 3 is 9, times 6 minus 5, that's 1. 9 times 1 is 9. And it's positive, so that means the interval from 5 to infinity will have positive f of x values. Now, this says greater than 0, meaning that it's positive. So I want to select the intervals that gave me a conclusion of positive values. Notice there are 2 of them. This one and this one. -infinity to -3 and 5 infinity. So that solution set will be this interval from -infinity to -3 union 5 infinity. That's the solution set here. And if I graph this on the number line, here's -3, here's 5. -infinity to -3 is this shaded area to the left of 3, and it does not include 3. And 5 to infinity, that's the shaded area to the right of 5, where 5 is not included. Okay? So that's how you would graph that solution set of a polynomial inequality. Okay? Alright, another example of just that would be this. Let's say we had x plus 1 times x minus 7 is less than or equal to 0. and we want to solve and graph that solution set on the number line. And notice that that particular polynomial inequality is already factored out for you, so we don't need to do any factoring. Okay. So here's that inequality, and it does say less than or equal to 0, so we're looking at things that are negative. So that's pretty much a good hint right there. All right, let's try to solve this if it was x plus 1 times x minus 7 equal to 0. And then we're going to set each binomial factor equal to 0. So we set x plus 1 equal to 0, and then set x minus 7 equal to 0. And then for each equation, we'll solve for x. So for x plus 1 equal to 0, you're going to have x is equal to negative 1. And then for x minus 7 equal to 0, you're going to have x is equal to 7. So negative 1 and 7 represent the boundary points on that particular number line. Okay, so here is negative 1. And here's 7. Now it says less than or equal to, so we're going to put closed circles at negative 1 and another closed circle at 7, because they're going to be included in our solution set. Okay, so we have 2 boundary points. That means we have 3 intervals that we're going to be looking at. 3 of them. So the column for intervals, my first interval will be from negative infinity to negative 1. The next one will be negative 1 to 7. Then the last one will be from 7 to infinity. Okay. Now, the next column is my test value. I'm going to pick a test value that I'm going to use for each individual interval. And then f of x. My f of x is always going to be that x plus 1 times x minus 7. That's this part right here. And then my conclusion. Okay. From negative infinity to negative 1, that's this interval right here. Let's use x equal negative 2 as a test value. I could have used negative 3 or negative 4, as long as that test value is a number that is within that particular interval. So if x is negative 2, in this problem, negative 2 plus 1, that's negative 1. And then negative 2 minus 7 is negative 9. And negative 1 times negative 9 is a positive 9. So here we came up with a positive value for f of x. So that means for that interval, negative infinity to negative 1, I'm going to have positive f of x values. The next interval is negative 1 to 7. That's this interval right here. Let's use 0 again, just like we did before. Here, 0 plus 1 is 1. 0 minus 7 is negative 7. 1 times negative 7 is negative 7. And again, that's negative, so that means that between negative 1 and 7, I'm going to get negative f of x values. And then finally, from 7 to infinity, that's this part right here, I'll use x is equal to 8. And then substitute 8 in for x, so 8 plus 1 will be 9. And 8 minus 7 will be 1. 9 times 1 is 9. And 9 is positive, so that means from 7 to infinity, my f of x values will be positive. Okay, now, let's take a look at the inequality that we were given. We were given less than or equal to 0, meaning that we're going to have negative values here. Anything less than 0 will be negative. So we want to select the intervals that gave us a negative f of x, a negative conclusion. There's only one. That's negative 1, comma 7. Now, notice that 1 and 7 are included in this solution set. So that means my solution set, this time we used a bracket around negative 1 and 7 to show that 1 and 7 are included in that solution set. I mean, negative 1 and 7 are included. So here's negative 1, and there's 7. And we'll put brackets around negative 1 and 7, and we shade in between. Okay, so that's the solution set for x plus 1 times x minus 7 is less than or equal to 0. Okay. So far we talked about how to graph a polynomial inequality. Well, solve polynomial inequalities. Now here's the other part, solving rational inequalities. Now, the procedure is pretty much similar with the exception of number 1 and number 2. Number 1, you're going to bring all terms to one side, obtaining a 0 on the other side. You want to express that rational function as a single quotient. Then step number 2 is to set the numerator and denominator of f equal to 0. And then the procedures for step 3, 4, and 5 for polynomial inequalities are pretty much going to be the same. Now I've added something very important. In a rational inequality, you must avoid any values of x that will cause the denominator to be 0 in your solution set. The reason for that is because division by 0 is undefined. Okay, so now let's look at an example of something just like that. Here we got x minus 6 divided by x plus 2 is equal to 0. And here we want to solve and graph the solution set. And by the way, this is an example of a polynomial inequality. Okay. Now notice that we already have a single quotient, so we don't need to do any type of manipulation or moving any terms to one side, and besides we already got a 0 on one side of this inequality. So all we need to do here is set the numerator, which is x minus 6, equal to 0, and set the denominator, which is x plus 2, equal to 0, and solve for x. So for x plus 6 is equal to 0, we can have x is equal to 6, and for x minus 2 is equal to 0, you're going to have x is equal to negative 2. So my two boundary points are going to be at negative 2 and 6. Now I have to be very careful here, because at 6 we're going to be okay, because that's in the numerator. But the denominator, we're going to have to exclude x equals negative 2 by putting an empty circle there. The reason for that is that's the value of x that will make your denominator 0 here. Okay? And we're going to exclude x equal negative 2 in our solution set. Okay, now step 3, 4, and 5 are the same. It's just simply creating that table, finding out what your intervals are. This first one is from negative infinity up to negative 2. The second one is from negative 2 to 6. And the third one is from 6 to infinity. Those are your three intervals here. And then a test value, and then f of x, and then the final conclusion, whether it's positive or negative. I need to move that over so y'all can see this. Okay, now from negative infinity to negative 2, that's this interval right here. Let's use negative 3. Okay, now let's look at this, the numerator and the denominator. Negative 3 minus 6 is negative 9, that's the numerator. The denominator is negative 3 plus 2, that's negative 1. Negative 9 divided by negative 1 will be positive 9. And it is positive, so I can say that the conclusion here will be that from negative infinity up to negative 2, I'm going to have positive f of x values. The next interval is from negative 2 up to 6. That's this interval right here. Let's use x equals 0, because that's much easier. The numerator is 0 minus 6, that's negative 6. The denominator is 0 plus 2, which is 2. 6 divided by negative 6 divided by 2 is negative 3. Here f of x is negative at x is equal to 0, so between the interval of negative 2 and negative 6, I'm going to get negative f of x values. And then from 6 to infinity, let's use x is equal to 7. Well, if x equals 7, 7 minus 6, that's 1. The denominator, 7 plus 2, is 9. So here I'm going to have 1/9. It's a positive number, so from 6 to infinity, I will have positive values for f of x. Okay, now, this says greater than or equal to, which means positive. So I want to select the ones that have positive conclusions here. This one and this one. Now, let's be careful how we write the solution set as our final answer, because at 2, we know the denominator is going to be 0, so we cannot include, actually we can't include negative 2, because we'll get a 0 in the denominator, so this will be negative infinity to negative 2 with the parentheses here. 6 won't be a problem, but 6 it will be included, so we use a bracket, 6 infinity. Okay, does everyone see this? Even though it says greater than or equal to, in a rational inequality, we have to exclude the negative 2, because we will get a 0 in the denominator. We can include the 6. So in this case here, is negative 2. This is 6. And at 6 to infinity, we use a bracket at 6. And we shade everything to the right of 6. Now from negative infinity to 2, we use the parentheses at negative 2 and shade everything to the left. Okay, so that's how you'll graph that solution set for x minus 6 divided by x plus 2 is greater than or equal to 0. Okay, now I think I got another polynomial inequality. Well, rational inequality, I should say. Let's say we want to solve and graph the solution set x plus 5 divided by x plus 2 is less than 0. X plus 5 divided by x plus 2 is less than 0. Now I'll leave this up here. Alright, in this case here, it's already factored. We have a single quotient, and we have a 0 on the other side of that inequality symbol. So we'll go ahead and set the numerator, which is x plus 5, equal to 0, and set x plus 2 equal to 0. Each one of those will solve for x. So for x plus 5 is equal to 0, that'd be x equal to negative 5, and x plus 2 equal to 0 means x is equal to negative 2. So my two boundary points are 5 and negative 2. Now those boundary points will be excluded in our solution set because the inequality says less than. Let's see, here's negative 2, That's -5. And I'm drawing empty circles at -5 and -2 to show that those two values are not included in this solution set. So in this case here, we have 3 different intervals. Here's 1, 2, and then 3. And those intervals are, the first one's from -infinity up to -5. And then the next one's from -5 to -2. And then the last one's from -2 all the way to infinity. And the next column is going to be my test value. And then I'm going to evaluate f of x using my test values and then come up with my conclusions, whether they're positive or negative. All right, from -infinity up to -5, that's this interval right here. Let's use -6 as a test value. Okay, and when I do that, I'm using this as my f of x. So here, -6 plus 5 is -1. The denominator is -6 plus 2. That's -4. So I got -1 over -4, or just 1/4, which is positive, because negative divided by negative will give me a positive. So that means my conclusion for that interval, I'm going to have positive f of x values for -infinity up to -5. All right, for -5 to -2, that's this interval right here. Let's use x equals -4. And if x is -4, -4 plus 5, that will be a positive 1. The denominator is -4 plus 2, that's -2. Well, 1 over -2 would just be -1/2. And anyway, it's going to be negative, so between -5 and -2, I'm going to have negative f of x values. And then finally, from 2 all the way to infinity, use 0. So here 0 plus 5 is 5. The denominator is 0 plus 2, which is 2. So this is 5/2, so we're 2.5 is positive. So from 2 to infinity, I'm going to have positive f of x values. Now, the inequality that I started off with is less than 0, meaning negative. So I want to choose the intervals that gave me a negative conclusion. There was only one. That's from -5 to -2. So in this case here, my solution set is going to be the interval from -5 to -2. And when I graph this, that's -5, that's -2. I'm going to use parentheses at -5 and -2 because they're not included. And I'm going to shade in between. Okay. So that's pretty much how you graph a polynomial, well, a rational inequality. And that would conclude this particular section on polynomial and rational inequalities.